What if we colonized Mars, not in science fiction, but as a real, engineered system that has to work every hour of every soul? How would ships, habitats, power, water, food, and economics interlock? And what would it cost, change, and demand from Earth? To make it real, we have to build a colony like a factory, manage it like a power grid, and feed it like a closed-loop city. Mars is cold, thin-aired, and dry. Average temperatures hover near -60 Celsius, and surface pressure is under 1% of Earth's. Its atmosphere is mostly carbon dioxide with traces of nitrogen and argon, offering negligible shielding from radiation and no breathable oxygen. Radiation exposure on the surface is significantly higher than on Earth, demanding robust shielding in habitats and vehicles. Transfer windows open roughly every 26 months, setting the cadence for cargo and crew flows and creating long logistical cycles. Moving mass to Mars is expensive in delta V and dollars, so the colony must maximize in-situ resource utilization from day one. That means harvesting ice for water, splitting it for oxygen and hydrogen, and turning Martian rock into building material and metal feedstock. Power will come from a mix of solar arrays with dust mitigation, compact fission reactors for baseload, and batteries or flywheels to ride out storms and nights. Initial flights send uncrewed cargo, power units, ISRU skids, excavators, habitat shells, and life support racks. Robotic teams deploy solar mats, position radiators, and connect trunks to a central power and data spine. A compact reactor is buried and burmed, routed through heat exchangers and conversion units to provide reliable baseload electricity. ISRU units split CO2 into oxygen and carbon monoxide, and split ice into oxygen and hydrogen, building propellant reserves and breathable air. Shallow ice deposits near mid-latitudes provide water with manageable drilling, filtration, and decontamination steps. Inflatable modules are covered with regolith using bulldozer blades and conveyor hoppers to cut radiation and thermal swings. Life support runs on redundant loops: CO2 scrubbing, humidity control, oxygen balancing, and thermal regulation with failover paths. The first crews step into a functioning outpost, not a blank slate, immediately training on maintenance, emergency drills, and procedures. Daily life follows the numbers: power budget, heat rejection, water balance, oxygen partial pressure, and nitrogen buffer levels. EVAs are scheduled like factory maintenance: suit diagnostics, umbilical tests, tool manifests, and comms windows aligned with satellites. A small relay constellation keeps line of sight with rovers and base, routing data through deep space networks with minutes of delay to Earth. Dust management is relentless. Electrodynamic shields, air showers at airlocks, and filter swaps keep systems within spec. Early food is prepackaged, but pilot hydroponics and microbial protein units test water recycling and nutrient loops for scaling. Materials come from Mars. Sintered bricks, sulfur concrete mixes, and refined metals from regolith enable spare parts and shielding blocks. Crew health is tracked with bone density scans, radiation dosimeters, and psychological check-ins to prevent small issues from compounding. Every critical system has redundancy and manual bypasses. Crews train to isolate faults, swap modules, and keep the loop closed. By the end of the first year, the outpost behaves like an industrial plant that happens to host people, stable but never hands-off. The colony reshapes local microclimate inside domes and bermed modules, but leaves the external environment largely unchanged. Dust storms still dominate risk planning, reducing solar yield and forcing the base onto stored energy and fission for days or weeks. Ice wells require strict contamination control, with closed-loop water handling to avoid brine seepage or volatile loss. Waste streams are processed through membrane bioreactors and UV sterilization, recovering water and nutrients into agriculture. Greenhouse conditions remain confined to pressurized spaces. No planet-scale terraforming is attempted. Erosion control, berm stabilization, and dust suppression keep local terrain impacts contained to a few square kilometers. Infrared surveys confirm heat rejection is visible but limited, managed with radiators sized to avoid thermal shock cycles. Mars colonization only starts when launch costs drop. Heavy lift is routine, and in-space refueling closes the transport equation. Early years are capex heavy: power units, habitats, and ISRU. Later, operating costs dominate: maintenance, spares, and crew rotation. On Earth, the supply chain spans ports, factories, clean rooms, test stands, and launch pads synchronized to interplanetary windows. Insurance products evolve for deep space assets, pricing failure modes like EDL loss, reactor downtime, and habitat breaches. Mars exports little mass at first. It exports value as data, geology, engineering practice, autonomy software, and closed-loop know-how. A global contractor network feeds standard parts and certified modules, pushing interoperability across agencies and firms. Unit costs fall as production scales. Standardized modules cut assembly time and on-Mars commissioning risks. Inside the colony, rationing gives way to scheduling and markets for time and tools. Work orders, spares allocation, and printer queues become the backbone of a small but functional internal economy. The Mars base runs a microgrid with priority tiers: life support first, then comms, then industrial loads, then comfort. Low air density makes convection weak, so radiators and phase change storage move heat to the night sky efficiently. A layered comms stack manages local mesh networks, orbital relays, and deep space links with scheduled high-gain passes. Robots do heavy work: excavation, hauling, array cleaning. Humans supervise, step in via teleops for precision tasks. Predictive maintenance watches vibration, temperature, and flow rates, scheduling repairs before the red lines. Pressurized rovers extend reach to science targets and resource sites, supplied by small depots and waypoints. Additive manufacturing makes fittings, brackets, valves, and later complex spares. CT scans verify integrity before deployment. Safety is layered: pressure compartments, isolation doors, portable scrubbers, and safe rooms with independent oxygen and comms. Schedules anchor life: maintenance in the morning, science and fabrication mid-sol, workouts, and delayed calls home. Lower gravity demands regular resistance training and careful nutrition to protect bone density and cardiovascular health. Shared meals, quiet corners, and structured privacy reduce stress in confined habitats. Governance starts procedural: safety-first rules, rotation rights, duty rosters, and transparent incident reviews. Cross-training ensures everyone can cover critical systems: power, water, air, med, and fire response. A culture of checklists, quiet confidence, and care for each other keeps the system human as well as functional. Outside remains inhospitable. Inside feels like a ship: engineered, finite, and worth maintaining. Earth's networks stretch to Mars. Data latency reshapes software, operations, and how we collaborate across planets. Once the outpost stabilizes, growth becomes modular: duplicate power blocks, add greenhouses, and extend pressure tunnels. Population scales from dozens to a few hundred over a decade, pacing with power, water, and emergency capacity. Food shifts to a hybrid model: high-efficiency hydroponics, algae-derived proteins, and stored earth imports as buffer stock. Manufacturing matures to make most mechanical spares and some electronics assembly, with critical chips still imported. Structural methods diversify: regolith block walls, composite ribs, and better pressure bulkheads reduce reliance on shipped shells. A simple road system, beacons and depots allow safe travel to resource and study zones within a few hundred kilometers. Training centers institutionalize knowledge, so turnovers don't reset the learning curve. Medical capability expands to handle more procedures locally, reducing dependence on Earth for anything but the most complex cases. The supply loop runs on a 2-year drumbeat, with inventories and spares levels sized to absorb missed flights. On Mars, propellant depots stock oxygen and methane from ISRU, supporting surface vehicles, and eventually, ascent vehicles. Return cargo is light: samples, worn parts for forensic analysis, and experimental products for qualification. A governance charter codifies safety, environmental stewardship, research integrity, and crew rights. Rituals mark milestones, not spectacle, but the quiet acknowledgement that sustained operations are possible. Resilience comes from design. Isolate, reroute, repair. Every major failure has a playbook and a drill schedule. A months-long dust event forces baseload reliance and strict rationing. Agriculture shifts to low-light crops and stored reserves. Medevac may be impossible for long periods. Protocols favor stabilization on-site, with remote specialists advising. Fire risk is managed by compartmentalization, clean agents, and strict materials controls. Buffers of critical spares cover reactor coolant pumps, air filters, valves, and suit components. Tolerance for boredom and procedure wins. Mars rewards patience backed by engineering. Colonizing Mars is not a conquest. It is a systems project that teaches us how to live carefully within limits. Closed loops on Mars mirror what Earth needs: efficiency, redundancy, and respect for constraints. Maintenance becomes culture. Checklists become language. Reliability becomes ethics. Knowledge flows back to Earth. Better grids, better recycling, better ways to cooperate across distance. A colony that stays boring most days is a success, because boring means systems work. Mars will never be easy, but it can be livable, purposeful, and worth the effort. If we colonize Mars, we will do it the way we build power plants and hospitals, carefully, redundantly, and with humility for the environment that hosts us. What scenario should we explore next? Share your ideas below. You've been watching IfVerse, where imagination meets possibility. See you in our next reality.